Hey guys, what's up? Welcome back. I think everybody probably be here pretty soon. I sent out an email. I'll post that link every day on Moodle for the live stream. I'll also post the link in Discord. And today I sent out an email just to make sure everybody saw the live stream. So obviously, if you're here, you see it. But that's what I'll do pretty much every time. So. Are there any questions really before we get started? Back into 12.2. Does anybody have any questions? You could just type them over in the chat if you have any questions in particular. Just give everybody a second maybe to get here. Maybe they just got the email or whatever. So. Audio is not working in the chat. I have it on my end. Yeah, I have audio on my end. Okay, sweet. Cool. I posted the web work, the homework on Wednesday. Really? Here in double. It's weird. I think I only have the one microphone on. Yeah, just one. It's weird. Is anybody else here in double? It's a little strange. Oh, okay, phew. All right, cool. Well, let's get back to it then. 12.2 continued. So this is all about vectors. So 12.2 continued. And we started last time, or we ended last time with vectors. And we were looking at geometrically how to add them, subtract them, what they are. They're basically like directed line segments. And the length of the line segment is the magnitude of the vector, and the direction is indicated by the arrow on that line. But sometimes it's good to represent these vectors in a coordinate system. So we can work with vectors algebraically. So we can represent vectors algebraically. With a coordinate system. So if we look at maybe like the XY coordinate system, and we throw a vector in there, vector v, well, it's going to be a certain amount in the x direction, so call it v sub x, and a certain amount in the y direction, call it v sub y. So whenever we have a vector in 2 dimensions, it has 2 components. It has an x component and a y component. How far to go over in the x direction and how far to go over in the y direction. And then we represent that vector v using these angle brackets. And then the first component v sub x and the second component v sub y. So very similar to a point, except we use angle brackets, and that denotes a vector that goes from the origin out to that point. All it really means, though, is wherever you start, go so far in the x direction and then so far in the y direction. So for example, let's say we had the vector starting at the point 3, 1, and the vector v is the vector 1, 1. So say the vector v is the vector 1, 1, and the tail is at the point 3, 1. Where's the tip? So the tip is at, well, I go 1 over in the x direction. Actually, that's a little big. There we go. Where's the tip? Well, the tip's going to be at 4, 2. So here's your vector v. It says go 1 over in the x direction, 1 up in the y direction. That puts our tip at the point 4, 2. So the vector v is the same vector. It's the vector 1, 1. No matter where you put the tail, it's just saying, okay, go that far in the x direction and then that far in the y direction, and you'll end up at the tail, or sorry, at the tip of the vector, starting at the tail. And you can place that tail anywhere you want. And if you place it at the origin, you'll end up at the point whose coordinates are the components of the vector. In 3 dimensions, we can have a vector, so we can also represent 3-dimensional vectors with components. So we have a vector v. It's going to have an x component, v sub x, a y component, v sub y, and a z component, v sub z. So it's basically the same thing. You go so far in the x, y, and z directions. And just note, we already kind of alluded to this, but just note the vector is the same no matter where we place the tail. So if it's the vector 1, 1, like in our example, it doesn't matter where we put the tail. The vector 1, 1 is always going to point in the same direction and have the same length. So you could kind of visualize that like this. So the vector 1, 1 look like that. But could also place the tail anywhere else. It's the same vector. But when we do place the tail at the origin, we say the vector is in standard position. So that's just something to keep in mind. It's the same vector no matter where we place the tail, but if we do put the tail at the origin, we say that we put the vector in standard position. So now we can define a vector between 2 points, basically knowing that the tail starts at one point and the tip starts at the other point. I just need to look at the change in x, the change in y, and the change in z. So I can define a vector that goes between 2 points based off our intuition. So definition, given 2 points, A, which is x1, y1, z1, and B, which is x2, y2, z2, we define the vector AB, which goes from A to B to B, vector AB equals x2 minus x1, y2 minus y1, and z2 minus z1. So that will be the vector that goes from A to B. If you are to put the tail of this vector on A, the tip will be on B. So the tail of AB put at A will result in the tip ending at B. So that's how you define a vector between 2 points in 3-dimensional space, or even 2-dimensional space. You just have to drop the z component. But yeah, it doesn't matter either one, 2 or 3-dimensional space. Right. Just take a second. Try not to go too quickly. See if there are any questions. Okay, another definition is the magnitude or the length of a vector. It's a definition. The magnitude or length of a vector is defined by almost like absolute value around the vector. Call it the length, the magnitude, or the modulus of the vector. And if it's 2-dimensional, it's vx squared plus vy squared. Take the square root. And that's really just Pythagorean theorem. So if you look at it in 2 dimensions, you have vx, you have vy, and you want to get the length of v, which is the hypotenuse. It's really just the Pythagorean theorem. And then similarly, in 3D, magnitude of the vector would be square root vx squared plus vy squared plus vz squared. So this is for 2 and 3 dimensions, respectively. So that is the magnitude of a vector. So that's how you find the length of the vector, or how strong is the magnitude. Let's see. Adding, subtracting, multiplying vectors with scalars. So algebraic operations for vectors. So algebraic operations for vectors. So addition, we'll just say two-dimensional vectors, but the same thing is for three-dimensional vectors. We'll say let u equal u1 comma u2 and v equal v1 comma v2. Then u plus v is defined to be, algebraically at least, u1 plus v1 comma u2 plus v2. And u minus v is defined to be u1 minus v1 comma u2 minus v2. So you just subtract the corresponding components, or add them, depending on what you're doing. And if c is a scalar, a constant, if c is a constant, then c times u would be equal to c times u1 comma c times u2. So that's how we define addition, subtraction, and scalar multiplication. So let's look at some examples. There shouldn't be a 2 on the C. Sorry. Okay, let's look at some examples here. So example, I'll let the vector A be the vector 5, negative 12, and let the vector B be equal to negative 3, negative 6. Find A plus B and the magnitude of 2A minus 3B. So the first one, A plus B, pretty easy. Just add those two together. A plus B. Add the corresponding components. It's going to be 5 plus -3, and -12 plus -6. And that's going to end up being 2, -18. So that one's pretty easy. Now we need to find the magnitude of the vector 2a minus 3b. Well, what's 2 times a? 2a is going to be 2 times 5, comma, 2 times -12. Which is going to be 10, comma, -48. 24. 10 comma -24. And then also let's look at 3 times b. So 3b is going to equal 3 times -3 and 3 times -6. And that's going to give us -9, -18. And now we need to do 2a minus 3b. So 2a minus 3b is going to be 10, comma, -24 minus -9, comma, -18. Which is going to end up being 10 plus 9, comma, -24 plus 18. And let's see, that's going to be 19, comma, -6. And now I need to find the magnitude of that. So magnitude of 2a minus 3b is going to equal square root of 19 squared plus -6 squared. And then 19 squared is what? 381? Let's see. $369. 361 plus 36. So that's going to be square root of 397. And that is our answer. Questions? Yeah, I know this stuff is a little easy here early on, especially till we get to like 12.5. But yeah, just want to make sure I'm not going too fast. Feel free to ask questions. Okay, cool. In general, we can have any dimensional space we want, at least mathematically. Maybe not physically, but mathematically we can. So in general, we can have n-dimensional vectors v in what we call Rn. And those vectors have n components, v1, v2, v3, ... vn. And this is super useful in, well, a lot of areas of engineering, numerical simulations for engineering. Also super useful in computer science with machine learning and things like that. These algorithms that you talk about in computer science talk about feature vectors, and you can have as many features as you want. You want to study correlations and things like that between different independent variables. Well, those independent variables make up your n dimensions, and so you can have n-dimensional vectors in real-world applications, even though it's not like spatially. Doesn't have to be spatial, but regardless, there are some properties that hold for any dimensional vector, and we've seen a couple of them already. So properties of vectors. And those properties are, first one is that a plus b vector addition is equal to b plus a. And we saw that yesterday, well not yesterday, last time, with the parallelogram law geometrically. And we can see that it's pretty easy to do with components of vectors as well. So that's what we call the commutative property for addition. And pretty easy to wrap our mind around. Doesn't matter which one you add first, which one you write second. The second property is that a plus b plus c is equal to, so adding b and c first and then adding a to that is the same as adding a and b first and then adding c to that. And that's what we call the associative property. The next one is there's a neutral element for addition called 0. So a plus a 0 vector equals a, and the 0 vector is such that every component is 0. The next property is a plus -1 times a equals 0 vector. And that -1 times a, we often write that as -a. So it's an additive inverse. Number 5 is that scalar multiplication distributes over vector addition. So we'll say gamma times a plus b is equal to gamma times a plus gamma times b. So here gamma is just a scalar. And I'll just stop here with number 6. And we'll say that beta plus gamma times vector A is equal to beta times A plus gamma times A. So basically, vector scalar multiplication onto vector distributes over scalar addition on the right. So we're not too worried about these properties. They're pretty intuitive. I don't think you're going to have a hard time understanding them. I'm not going to harp on them too much, but just throwing them out there. These are really the properties of vectors that define vectors mathematically. Physically, we defined vectors with a magnitude and a direction, but this is mathematically more of the definition. There are 2 more properties, but I'm going to skip them. Basically, you can multiply a vector by 1 and you get the same vector. And scalar multiplication is associative, so I'm not going to worry about those. Okay, I want to slow down, make sure I'm not rushing through. Of course, as always, just post any questions in the chat and I'll answer them. Okay, definition. In 2-dimensional space, we'll call it R2. In 2-dimensional space, we have, or we should say we define, 2 standard basis vectors I hat equals 1, 0 and j hat, which equals the vector 0, 1. In R3, we define 3 standard basis vectors I hat equals 1, 0, 0 j hat equals 0, 1, 0 and k hat equals 0, 0, 1. And if we graph these, they just lie along the coordinate axes. So I hat is along the x direction, j hat is along the y direction, k hat is along the z direction. And I like to say hat just to denote that it's a very special vector. It's along a coordinate axis and its magnitude is 1. So note, magnitude of I hat equals magnitude of j hat equals magnitude of k hat equals 1. So if you were to square the components and add them together, you would just get 1. And then taking the square roots, you would get 1 again. So these are what we call the standard basis vectors. And it's important to note any vector v equal to vx, vy, vz can be written in terms of I, j, and k. And the way we can do that is we can say that v is equal to vxi plus vyj plus vz times k. Because I is just 1, 0, 0, so that would be the vector vx 0, 0 plus 0 vy 0, multiplying j by vy, and then plus 0, 0 vz when I multiply k by vz. And then adding those together, we get vx, vy, vz. So any vector can be written in terms of these standard basis vectors. Of course, the same is true in 2 dimensions. So basically just take the components x, y, and z and multiply them by I, j, or k, depending on which component you're looking at. All right, let's look at another definition. So definition. A unit vector is a vector for which the magnitude is 1. For example, I, j, and k are unit vectors. They're just very special unit vectors in that they lie along x, y, and z axis. Another example, though, is that the vector v equal to 1 over square root of 2, comma 1 over square root of 2 is also a unit vector. Because you can take the magnitude of v, which is the square root of 1 over square root of 2 squared plus 1 over square root of 2 squared. You get square root of 1/2 plus 1/2, which is square root of 1, which is 1. So that is another vector that is a unit vector. Again, are there any questions so far? Okay, cool. Keep moving on. Just a few more things here today for this section, then we may get to 12.3. If not, it's no big deal. I'm not worried about rushing through early on for sure. I have plenty of time to catch up. Wouldn't really say we're behind anyway, so let's think about this question. Given any vector v, let's just say this is our vector v. How can I make v, or what can I do to v to make a unit vector in the same direction as v? So v has some magnitude, and we'll call this thing u. So how do we create a vector u such that magnitude of u equals 1 and u is in the same direction as v? So how do we create a vector that has unit magnitude and is in the same direction as our original vector? Well, we know to change the length of a vector v, we just have to multiply it by a scalar. So we need to multiply. So the answer really is multiply v by a scalar. But which one? So which scalar? Well, v already has a length, and if I want to make that length shrink down to 1, I need to basically eliminate that length. I need to normalize it, basically. Need to make that length become unit length. So it has a length. I want to multiply by a scalar. Well, I basically need to multiply by 1 over the length that's already there. So multiplying v by 1 over magnitude of v will create a unit vector in the direction of v. So you could say u, which is 1 over magnitude of v times v sub x comma v sub y. Let's just say if I'm in 2 dimensions. Then the magnitude of u would be square root of v sub x over magnitude of v squared plus v sub y over magnitude of v squared, which would be square root vx squared over magnitude of v squared plus vy squared over magnitude v squared, which would be square root of vx squared plus vy squared over magnitude v squared, which is square root of x squared, or vx squared plus vy squared over magnitude of v, which is magnitude of v over magnitude of v, which is 1. So dividing a vector by its magnitude creates a unit vector in the same direction. So for example, find a unit vector in the same direction as the vector -4, 2, 4. So what we need to do is take the magnitude of this vector and then divide by the magnitude. So the magnitude of -4, 2, 4 is going to be square roots -4 squared plus 2 squared plus 4 squared, which is square root of 16 plus 4 plus 16, which is 32 plus 4, which is 36. So square root of 36, which is 6. So then our unit vector u is going to be 1 over 6 times the vector -4, 2, 4, which is the vector 2/3, or -2/3, 1/3, 2/3. So just have to multiply the vector by 1 over its magnitude. Then we have a unit vector in the direction of the original vector. Let's look at another example. If v lies in the first quadrant and makes an angle of pi over 3 with the positive x-axis, and the magnitude of v is equal to 4, find the components of v. So let's see what we got here. We got an angle of pi over 3. And I want to find the components of this vector, vector v right here. Well, I know that the length is 4, so I have the hypotenuse already. How can I get the x and y components? So this length right here is already 4. Well, what do I know? I know from trigonometry. That v sub x is going to be magnitude of v times cosine of theta, which is going to be 4 cosine of pi over 3, which is 4 times 1/2, which is 2. And v sub y is going to be magnitude of v times sine theta, which is going to be 4 sine of pi over 3, which is going to be 4 times square root of 3 over 2, which is 2 square root of 3. So in component form, v is actually, let's see, 2 comma 2 square roots of 3. So just using some trigonometry there to get the components given the magnitude and the direction angle. So that angle off the positive x-axis. And just a quick note, if theta is given as a positive angle off the positive x-axis, then a unit vector in the direction of theta is u equals cosine theta comma sine theta, because that would be anything on the unit circle basically. So that's a good thing to keep in mind. If you need a unit vector in the direction of some angle, theta, off the positive x-axis, then you can just take cosine theta comma sine theta. I guess it doesn't have to be a positive angle. It just needs to be off the positive x-axis. If it's not off the positive x-axis, maybe it's off the y-axis, you just have to figure out, okay, what's the complementary angle or supplementary angle to get you off of the positive x-axis. And they can use sine and cosine that way. Or you can just do your trig. You know, if you're really good with trig and you want to work off the y-axis, that's fine. Doesn't matter. But this is the way I do it. I like to do off the positive x-axis using sine and cosine this way. And maybe one more example for this section here is, let's see, find the magnitude of the resultant force. So example, find the magnitude and direction of the resultant force. So I'll give you a diagram and then we'll find the magnitude and the direction of the resultant. So I got two forces here. I'm going to just graph them. The first force is 200 newtons this way. And that angle that it makes right there is 60 degrees. The second force is along the x-axis, actually along the negative x-axis. And it's being 300 newtons. So it should actually be longer, but kind of ran out of space. So let's make it a little thicker. It's a stronger force pulling to the left than there is pulling up at a degree of 60. So where do you think the resultant force is going to be? Well, probably somewhere between the two. My guess is something like this. So when you add those two forces together, it's probably going to be something like that. So we had F1, we'll call it F1, force 1 and force 2. And then the green one is going to be the resultant. So F1 plus F2. We can do it graphically, but now let's do it algebraically. Really find the components and do all that stuff. So F1 is actually going to be 200 times cosine 60 comma sine 60. And F2 is going to be 300 cosine of 180 comma sine 180. And so cosine of 60 we know is 1/2, so this is going to be 100 comma 100 square roots of 3. And this force is in newtons. And then here, cosine of 180 is -1, so negative 300 comma 0. And so F1 plus F2 is going to be negative 200 comma 100 square roots of 3. And just like we predicted, that does point towards quadrant 2, negative x, positive y. And now what's the magnitude of this resultant? So the magnitude, so this is the resultant force right here. So this is the resultant force. And we're told to find the magnitude of this and the direction. So now magnitude of this resultant, I'll call it f sub r. It's going to be square roots of negative 200 squared plus 100 square roots of 3 squared, which is going to be square root of 70,000. And just for a decimal approximation, that's about 264.58 newtons. So they kind of don't really add up very well. Like one is 200, one's 300. You would think the best you could do, of course, is to get 500. Well, we're getting better than 200, but we're not getting more than 300 because they're not like adding up, because they're kind of pulling against each other. So let's find the angle theta that's made. Well, that's going to be the arctan of the y component over the x component. So arctan of 100 square roots of 3 over negative 200 plus 180 degrees, which is 139.11 degrees. So kind of like we expected, it's an angle in quadrant 2. So that's a quadrant 2 angle, just kind of like we expected. Any questions about that example? I know it's kind of going in a new direction, but if you had your intro statics course, you know, freshman engineering, you should have seen something like this, as well as Physics 201. You probably covered some of the same topics already, but we just want to go through it again, get more of a mathematical understanding of what's going on. So any questions before we move on to 12.3? You guys are extremely quiet. I'm not sure if it's because I've only had a few of you, or if it's just because it's 8 o'clock in the morning, but you guys are extremely quiet. Don't be afraid to ask questions. Or just whatever. You know, some people just post dumb stuff in the chat, which is fine. But yeah, don't be afraid to ask questions. Why do we add 180 when decrease? Oh, okay, good question. So arctan has a range of negative 90 to positive 90. If we go back to arctangent, its graph, you know, looks like this, but it's bounded between negative pi over 2 and pi over 2. So its range, so the range of arctan x is negative pi over 2 to pi over 2. But we know this angle is going to be in quadrant 2. We're not looking at a negative angle. We are looking at the resultant force over here. And these two forces are not going to give me anything in quadrant 4. Like, that's guaranteed. And we're going to assume positive angles between vectors. So another note is, well, I don't worry about that right now. So range of arctan x is between negative pi over 2 and positive pi over 2. And graphically, when we add the two vectors, we see the sum will be in quadrant 2. So arctan of a negative number actually gives us a negative angle. And so to get from quadrant 4 to quadrant 2, I have to add 180. So arctan of 100 square root of 3 over negative 200 is in quadrant 4 as a negative angle. So to get to quadrant 2, I have to add 180 to get up there. It's a good question. Other questions? Okay, we have 7 minutes. We'll introduce the dot product, maybe write down some of the properties, but we won't really spend a whole lot of time today. But let's just define it at least, maybe look at an example and or look at the properties. So definition. Whoops, let me move to a new section, 12.3. 12.3. This is called the dot product. And then we define the dot product as, let's say, if vector A has components A1, A2, A3, and B has components B1, B2, B3 are vectors. So if A and B are vectors, then the dot product A dot B is defined by A dot B equals a1b1 plus a2b2 plus a3b3. So you just multiply the corresponding components and then add them all together. And this actually works in any dimension, 2 dimension, 3 dimension, n dimensions. You can just multiply the corresponding components of the vectors and add them together. For example, so find the dot product. A dot B if the vector A is -2, 1, 0 and the vector B is 1, -3, 3. Not too hard. A dot B is going to be -2 times +1 plus 1 times -3. That's a 1, sorry. Kind of looks a little funny. It's a 1. 1 times -3 and then plus a 0 times 3. And that ends up being -2 minus 3, which is -5. So this is our definition of the dot product. You will have seen probably in Physics 201. The other definition of the dot product, we're going to talk about that next time. But they're related. And it's actually law of cosines that relates them. We won't go through all of that, but they are related, and it's through the law of cosines. So now I'll just throw up a few properties of the dot product, and we'll call it a day. So properties of the dot product. And the first one is that A dot A is really just the magnitude of A squared. That's interesting. Second one is A dot B equals B dot A. So this thing is what we call symmetric, or you could call it commutative. So A dot B equals B dot A. Number 3, constant gamma times A dotted with B is the same as keeping the constant outside and doing the dot product of A and B first. Next property is the 0 vector dotted with A. It's just going to be the 0 scalar. And then number 5, A dotted with vector B plus vector C is equal to A dot B plus A dot C. So the dot product distributes over vector addition. So it's kind of like a vector multiplication. It just produces a scalar, a number. So the dot product is a number. So sometimes we call it the scalar product or the inner product, but it just produces a number if you have 2 vectors. Cool. 1 minute to spare. We'll call it a day. If there are any questions, feel free to ask. I'll hang out for a minute, see if anybody has any questions. Otherwise, we'll call it a day. You can get started on the homework. And I'll see you guys again on Monday. Like I said, I'll have links always on Moodle and on our Discord channel to the live stream. So have a good weekend. I'll talk to you guys later.